when you talk about encryption, it's good to have the proper terms in mind when you're referring to things. So if you're using ciphers or exotic algorithms to scramble the content, the digital content, to encrypt something or decrypt something, that discipline is referred to as cryptography. And if you're breaking the codes, that's called cryptanalysis. Together, cryptanalysis and cryptography are generically referred to as cryptology, right? Which is an important distinction, and those are related terms. Like you've heard of astronomy and then astrology, right? And astrology has to do with Greek mythology and the signs of the zodiac and all that kind of stuff. You know, somebody's a Pisces or an Aries. You know what I'm talking about?
Yeah.
Yeah. And astrology is not related to astronomy, other than there are some constellations that share common names, like Cancer and Taurus and so on. But they're two very different topics. That's not true for cryptology. You know, cryptology has two main branches, cryptanalysis and cryptography. We're going to focus on the ciphers and encryption and decryption. And we're not going to get into much in terms of code breaking, but we will make some references to code breaking when we're talking about the kind of ciphers and how much easier it is to break some instead of others. So there are two basic forms of encryption. One is referred to as symmetric encryption, and that means that you have a single key, and it's often called single key encryption. The cipher that's used to input information, and by the way, before the information is encrypted, this is referred to as plain text. Okay, so when we say plain text, we're talking about unencrypted data. And then when we talk about ciphertext, that's the output of the cipher algorithm or the encryption process, right? So when we talk about ciphertext, that's the encrypted output. When we talk about plain text, that's the input. Now with decryption, it's kind of the reverse process. So it's easy to get confused. We take ciphertext and input the ciphertext to revert back to the plain text. So the plain text is the output for a decryption process using the same key or cipher, okay? Does that make sense?
Yes.
Okay. Now, symmetric encryption, in terms of basics, the Achilles heel is that there's a single key. So if you have a single key and someone gets your key, they can decrypt your messages. So the important thing to understand about single key encryption is that it's easy to implement, but the key security is the big problem or the big challenge, right? The sender and the receiver have to have copies of that secret key, and it has to be transferred between parties in a secure fashion, right? And what you're going to find out is that there's a neat solution when you pair symmetric encryption with asymmetric encryption, okay? The thing to understand about it is that encryption can be as easy as applying some simple mathematical functions to binary input, and then you get some junk out, and then if you plug the information back in, you get the original plain text. Now, we've talked about hashes before, and hashes also involve algorithms right? Or ciphers. The only difference is that regardless of the size of the input for a hash, the output is always the same discrete number of characters. And if you take those unique characters and stuff them back into the hashing algorithm, you do not get the original plain text back. What's interesting about a hashing cipher is that a hashing cipher, whenever there's any change to the binary input whatsoever, the slightest bit changes, then the output is completely different. I mean, radically different. So you can tell whether or not something's been modified, whether or not the data has integrity or it's been compromised, it's been corrupted, it's been changed, right? So ciphers are mathematical algorithms that are used to scramble the inputs and deliver some reliable and repeatable output. And generically, ciphers are those tools that make hashes work and make encryption work. But we want to draw that distinction between hashing and encryption very early in the process. Remember that hashes are good to detect if there's a change. So how is that significant? Let's say that you decided to email someone and we want to know that Raheem has sent a message that has not changed since it left Raheem's screen, right? Let's say Raheem is saying something really important, really powerful, really, really serious, like, hey, our data has been compromised on these systems. And we received that email from Raheem and we want to make sure, is that his true message? Or is somebody posing as Raheem, or did somebody capture his message and they've edited the message so that they create panic, right? So hackers do all kinds of things where they change and modify stuff. We use a hashing tool to ensure that something has integrity, it has not changed. But a hashing cipher is so different from an encryption cipher because you can reverse what you put in. If you feed the ciphertext back into the same key, you get the plain text back out. And so any questions about those excuse the pun, key distinctions?
No.
Okay. So here's just a simple graphic, right? You have the plain text, then you have the encryption algorithm. And so DES stands for Digital Encryption Standard. This has been retired. DES is no longer valid. I mean, it's still used in some places, but they found out that you can break it. It's been broken. So DES is no longer a valid standard if you want to keep things secret. AES, Advanced Encryption Standard, is now the new one. And there's a variation of DES that's actually still used, that's relatively secure. You take DES and you encrypt, then take the ciphertext, encrypt the ciphertext, then take the encrypted ciphertext and feed it into DES again so that you encrypt the ciphertext, which was encrypted from the ciphertext. It's called triple DES, 3DES. If you see the number 3 DES, that is still used in a lot of places, but it's still not as good as AES. We'll talk about those differences. So the key is the same on both ends. You have to have the key on the other end. You transmit the ciphertext so nobody can read your secrets. And then when it gets to the other end, the person that receives it uses the same key to unlock it to get the plain text back. Pretty simple, pretty straightforward. Now, when somebody wants to analyze the encryption cipher, there are some attacks that allow hackers to break the code. The cryptanalytic attack is the process of cryptanalysis I referred to earlier, right? So there's a lot of there's a rigorous study of the output versus the input, and there's a series of, well, they use supercomputers, right? So they can use supercomputers to try to analyze the input and the output to discern some kind of pattern between the input and the output, to try to infer or deduce, how does this encryption key work? With a brute force attack, we try all the possible keys until we get an intelligible translation into plain text. And what they're doing is they're trying all these different combinations of letters and words and numbers. And when they get an encryption result that's similar to what was captured, then they can assume basically it takes a lot of work. A brute force attack takes a long time, okay? So basically, at least half of all the possible keys must be tried to achieve success. And that's, that's a basic but really tedious process. There is a correlation between the size of the key. So when it comes to size, for symmetric, size does matter. Now, we're going to find out that when we're dealing with asymmetric encryption, there are very much larger keys, and everybody goes, wow, that must be really powerful. That's not the case for asymmetric. That's different. We'll get to that. But for symmetric, there are basically these three different standards. So here you see triple des, right? If you triple 64, you get the equivalent of a 168-bit key. Now that's because when you take a 64-bit key and you use it 3 times, but you're repeating the same encryption 3 times, you don't get 3 times 64. So 3 times 64 would be what? It's 192, right? So you'd think, oh, triple des must be 192. No, it has to do with the way they work that algorithm and the way they cycle that ciphertext back into DES. But here you see the plain text block size that goes in is 64 bits. What comes out is 64 bits. And the key size is 56 bits, right? Actually, okay. So what you get is the equivalent of 56 times 3. That's 168. My bad, okay? So if you take 56 times 3, then you get a 168-bit key because the original key was 56 bits. But once again, it's not like you get 3 times the power. So a triple des encryption is not as good as an AES. And AES, a 128-bit AES encryption is actually superior to a triple des 168-bit because of the way it's built. Now, what are the important things to understand about it? I want you to notice the pattern here. What goes in, plain text, you get as many characters back out, right? What goes in comes out. What goes in comes out. So the ciphertext, the size of the ciphertext matches the input size of the plain text, right? With a hash, it doesn't matter what the input size is. The output size is always just a few characters, right? So that's another telltale sign that you're dealing with a hashing algorithm instead of an encryption algorithm, okay? Yeah. So why do you see 112 here? There is a way to work with triple des where it's like twice as strong. 56 times 2 versus 3 times as strong. So there's two ways to work with triple des. The most effective one, of course, is the higher number. I think that very soon triple des will be broken and they'll have to, in fact, why don't we just look and see if triple des has been deprecated. So deprecated means retired, right? So it says, so this is NIST, Special Publication 800-131A. It says, for federal purposes, encryption using 3-key TDEA is deprecated through December using approved. Is it still considered? It is only considered secure if 3 separate keys are used. So triple des is deprecated for all new applications, right? So depending on the source and the standard, they're saying that, and this is all the way back in 2018, they're starting to retire this, right? So AES replaced it. Any questions about those first two standards?
No, sir.
Okay. So yeah, this was used everywhere, and then they figured out how to break it. When you see references to DEA, that's the acronym for the actual algorithm itself. But when it's used with ciphers as a method, then it's the DES label that applies, right? So when you see DEA, it's talking about the algorithm for DES. So the number of alternative keys when the key size increases is pretty dramatic, right? So if you have a 192-bit or a 256-bit key for AES, we're talking about a very, very long time to crack the key, to get the secret. It would take nation states thousands of years with the fastest supercomputer, that kind of thing. Okay.
Let's again talk.
Yes.
If it would take that long, how are people cracking it?
Well, that's a great question. So when DES, the algorithm, when the DEA algorithm was published, and by the way, they published the algorithms. So they published the algorithm so that people can try to crack it. And that's actually a best practice. It's counterintuitive, but they started using matrix computing. I want to say that there was a French graduate student that used a bunch of Linux machines, like a dozen Linux machines, and used them in a Beowulf cluster and teamed them all together and kind of created his own supercomputer. And after 18 months of working, cracked, or maybe it was a hashing algorithm. It might have been MD5. But a lot of times, because of advances in computing, what's happening is that the computer advances are part of that, but the other thing that's a piece of it has to do with the randomness of numbers. So another component of encryption that's very serious research in mathematics is the ability to create truly random numbers and very large random numbers. So some of the encryption algorithms incorporate a component that includes very large random numbers. And as computing capacity increases, the ability to work that into the algorithm increases, but then the ability to to perform cryptanalysis with the same computing resources, it's kind of a race. So the short answer is it's a race. Does that satisfy your question?
Yes.
Okay.
Yes.
So it's been said that if cars were the same as computing hardware, we could buy a Lamborghini Countach S for 25 cents. It would run 1,000,000 miles on a gallon of gas, and it would go from 0 to 500 in a tenth of a second or something like that, right? So those are fair comparisons. So they realized they'd have problems with DES, and they figured out a way to extend the utility of it by tripling it up, and that's the main takeaway from triple DES, right? Is that they found out that if you combined the algorithms, you could extend the use. And so this is the first practical example of where that was a big thing, right? So just before the year 2000, the National Institute of Standards and Technology said, hey, we need a new encryption standard to replace triple DES, and they had a big contest. Everyone repeat after me, Rindal.
Rindal.
Rindal, right? That's how you pronounce that spelling, okay? So Rindal had an algorithm that was published, and so there's a Federal Information Processing Security publication number 197. There's information about this. Has anyone ever heard of the company RSA?
No.
Okay, well, if you look into the history of this, it turned into a really big thing commercially because Rindal, I want to say RSA is part of that, but it uses a symmetric block cipher. So one of the other things I want to impress upon you about symmetric encryption or single key encryption is that there's two basic types, block and stream ciphers. And so far we've been talking about block ciphers. You take a block of plain text and what comes out is a block of ciphertext. And so DES, AES, triple DES, those are all block ciphers. But since this discipline has been launched, they've come up with algorithms that process streams of ones and zeros instead of discrete blocks. So let's see. I don't want to get into some weeds here. Here's the screen I want. Everybody can see this, right?
Yeah.
Okay. So block ciphers we've been talking about to this point. They process an input one block of elements at a time, and it produces an output block for each input block, and the keys can be reused. And this is the more common version of symmetric processing or symmetric encryption. Stream ciphers process each of the input elements in a steady sequence, right? Continuously. And it produces output one element at a time. So the stream comes out. The primary advantage is that they are almost always faster and use far less codes. So what are some examples of stream cipher application? Basically, if you encrypt streaming media where there's a lot of data, streaming ciphers are more efficient, right? So you're basically feeding the stream in one end and then encrypted stream comes out the other end. And so it encrypts and decrypts simultaneously. There are challenges with key management. because the reuse of keys is not as simple, right? So that's one difference between the two types of symmetric encryption methods or ciphers. So when I say, okay, of all the ciphers that exist, what are the three broad categories? We have hashing ciphers and we have encryption ciphers. And of the encryption ciphers, we have symmetric and asymmetric. And we'll talk about asymmetric in a minute. And I'll say, okay, of the symmetric cipher methods, that's the single key or same key method. What two types do we have for symmetric ciphers? And you'll say, oh, those are block or stream ciphers. So symmetric means same in, same out, basically. So when you're talking about a stream of characters and a stream of characters out, and on the other end, a stream of encrypted characters in and the stream of plain text characters out, it's just one after another instead of chunky blocks all at the same time. So one of the practical uses of encryption ciphers is that you can authenticate that messages are legitimate, right? That the contents have not been altered. And so you can include keys that allow you to validate the message. So only the sender and the receiver share the key, right? So when you're using symmetric ciphers for message authentication, only the sender and the receiver share the key. And this is a big deal, the fact that the message is authentic, it comes from the proper source, and the sequence of characters or words are valid. That's a big deal, right? So a lot of bad things can happen. There's a great t-shirt that says, "Let's eat, Grandma," and there's a comma. And then it says, "Grammar killed my grandma," right? And then there's another t-shirt that says, "Let's eat Grandma," with no comma. Same kind of thing there. So there are different scenarios where you can authenticate a message. Oftentimes when messages are authenticated with keys, it's not about scrambling the message, so it's confidential, but it's just to validate that the message is authentic because the key is unique and you get the key embedded in the message, and if the message is changed, the keys don't match. Does that make sense? Where in this case, we're validating that it's coming from that person, and you know it came from that person because the keys match, but the message itself is not encrypted. And so there are scenarios where you really only care about whether or not the sender is authentic, and you want to be sure it was them who sent it. So there are plenty of different and varied scenarios for how keys are used to authenticate messages and to encrypt information. The important thing to understand is that keys can be, here's the important thing to understand. Symmetric keys can be used to validate a message or to authenticate the source of a message. And that does not always automatically mean that the message that's sent is encrypted, okay? Does everybody understand what I'm saying? When an encryption key is used to authenticate a message, it's referred to as a MAC, which is not the same as a MAC address, the hardware fingerprint of a network interface, okay? Any questions?
No.
Okay, so if you see the term MAC, we're saying, okay, we're authenticating a message to make sure that it's coming from the same source. Not sure what's going on with this slide. This is a much busier diagram. And in this case, it talks about how the message transmission differs when you're using a symmetric key versus public key encryption, which is asymmetric. And I'm not going to get into that right now. Just understand that with symmetric encryption, the same key has to be on both sides of this for it to work. And that's a problem. That's a challenge. That's why public key encryption was devised. The most important thing. So that's what we're going to talk about next. Or, well, all right. So in terms of the order of the slide, it's going to talk about hashing functions. So SHA, secure hashing algorithm, SHA, is the most widely used hashing algorithms. There used to be a message digest, MD version 1, version 2, version 3, version 4, version 5, MD5, right? So hashes are useful when it comes to authenticating a login. So oftentimes hashes are used to store an encrypted value for a password. And because of the way the hash works, it's a secure way to store a value related to your password. When you enter a password, the same hash is used to generate a result. And if the hashes match, they know that the password was entered correctly. If the hashes are not, if they don't match, it means that somebody did not enter the password correctly. So this is how passwords are stored with hashes. Now you can pre-calculate hashes for password combinations, and this is called a rainbow table, okay? Has anyone ever heard of the term rainbow table? No? Okay, so if you have like 6 characters, numbers and letters and special characters, you can basically use a computer program to generate all of the different combinations of all the different letters and numbers and characters for a 6 character, 8 character, 10 character, right? And the number of combinations increases geometrically with the size of the password, the length of the password. But the hash that's created is the same size regardless. And if somebody's using a short password, basically it's very fast to crack it because you can have basically a limited collection of hashed password results, and it's pretty quick to do a lookup with a rainbow table. Okay. Of course, when you're doing a brute force attack, you're trying each combination to try to do that. But public key. All right, so we want to spend just a couple of quick minutes about public key. So because key storage and management was such a challenge with symmetric encryption, and the first work that was done with encryption in digital terms was with symmetric encryption. At a point in the mid 70s, so some decades later, somebody said, hey, working with the same key is causing a huge problem, because if the key gets away from you, then whoever has your key can decrypt your data. And the idea of a public key encryption method is that you have a public key and a private key. What is it you need to know that's most important about how this works? The two keys are related. So a public key and a private key are generated by the same algorithm, and they're separate and different but related. So you can use the public key to encrypt or decrypt what was encrypted or decrypted with the private key, and vice versa. But it's the public key that's the only one you give out for others to use. So in symmetric key encryption, there's a one-to-one relationship where only one person who's encrypting has a single key, and the only other person who is decrypting has a single key. And no one else can have the key, because if anybody else has the key, that means they can read the secret code, right? Does everybody get that?
Yeah.
With a public key method, you can give out your public key to anybody else. It's the private key that you keep. That's the one that can't get away from you. If anyone lays hold of your private key, you're screwed. But you can put public keys out there for anyone to use. And you might wonder, well, okay, I don't get that. Let's look at the browser. You remember I was talking about a certificate, right? Now I'm
Yeah.
going to oversimplify here, but a certificate is basically a package to store an encryption algorithm, a key, right? And if this is available on a public website, do you think it's the private key or the public key that's out here?
Public.
It's the public, right? Now, again, I'm oversimplifying, but in simple terms, this is really cool because you can distribute your public key to anybody and everybody. And if you send them something encrypted or signed with your private key, anybody who has your public key can say, okay, here is Chimera's public key. She sent something straight from her inbox using her private key. Let's see if it's really her. Because the public and the private key are related, you can use your public key and you'll get a green light. It'll check, right? So that's the trick. Now, you need some form of protocol for distribution. This last piece is the biggest aspect of this. So this diagram basically explains how this works, and it's reversible. So you can take Bob's, all right, so everybody sees Bob has a public key. So this is Bob over here, and this is Alice over here, right? And let's say that Bob needs to send something to Alice. What should Bob have to send something encrypted to Alice that Alice can read? Should Bob have Alice's private key or Alice's public key?
Maybe Alice's private key.
If Bob had Alice's private key, Bob could read everything that is supposed to be secret only to Alice.
Well, this will be the public.
Yeah, so Alice puts out her public key. See here, you see that Bob is giving out his public key to Alice, to Joy, to Mike, to Ted. So this is the only confusing part about public key encryption. And if you listen really carefully, you'll keep it straight, always. Bob has a public key, and he gives it to Joy, Mike, Alice, and Ted, right? When he sends something to Alice, he's using his private key because Alice has his public key. Just remember that the only person who has the private key is the person to which the private key belongs. And if Alice has to send something to Bob, and she doesn't have Bob's public key, right? So let's say that Alice has Bob's public key. Alice can use Bob's public key, encrypt a message that only Bob can read, and Bob gets it from Alice and he goes, oh, this is from Alice, and he used my public key. So I'm going to use my private key. So Bob uses his private key and he can decrypt the message that was encrypted with Bob's public key that Alice has to use. Same as Ted, same as Mike, same as Joy. So each of these people, if they have the public key, can send a private secret message to Bob. Everybody got that?
Yeah.
Now let's pretend for a second that Alice doesn't have Bob's public key. But Bob has Alice's public key. Okay, so let's say Alice doesn't have Bob's public key, but Bob has Alice's public key. Bob can take a message he intends only for Alice. He encrypts it with Alice's public key, sends it to Alice. Alice looks at it and she goes, I don't have Bob's public stuff. Oh, I see. He's used my public key. So she's able to open. The point about this is encrypted communication can originate from either Alice or Bob. All they have to do is share their public keys with other people. And if one person hasn't shared their public key, let's say Bob isn't sharing any keys, but he needs to send a private message to Alice. All he has to have is whose public key if he's sending it to Alice?
Alice.
Alice's public key, right? So even though Bob isn't doing anything with his public key, he can still send something private to Alice as long as someone has someone else's public key. That's the beauty of public-private key encryption. Now, we said earlier, and this is, we're going to be done in 60 seconds, okay? We're going to be done in 60 seconds. This last piece is the most important part. Some form of protocol is needed for distribution, okay? What we have, when you have the public-private key pair, is a whole system of distribution management called public key infrastructure, right? So what am I saying? The keys that we're talking about here, you can embed them in certificates. And if you take the certificates, you have a certificate authority that's called public key infrastructure. So let's see what it says here, all right? Public key crypto systems. So they have all these different kinds of crypto systems like RSA, and Rindahl is the R in RSA, okay? Diffie-Hellman, elliptic curve, DSS, these are all public key crypto systems. These are two key crypto systems, public and private key pairs. If you see RSA, Diffie-Hellman, DSS, elliptic curve, you got to memorize that. If you see AES, DES, triple DES, that's symmetric. So those are the basics. How do you manage all these public-private key pairs? You distribute certificates, okay? So in order to manage the public key distribution, what has evolved, and this is really innovative, is this idea of a public key infrastructure, or PKI. Now, you're probably asking, yeah, that sounds like a really complicated thing to do. Let me show you one thing real quick. Can everybody see my screen?
Yeah.
Okay, this is server 2022, right? And you know that the server operating system, Microsoft, they want to market to everybody. They want to be the general purpose server operating system that can do anything for anyone at any level for any size organization. Which means they designed some things about their operating system that make it a big target in terms of system security. But I want you to see this. I have my standard server operating system. I've downloaded from the Microsoft downloads in our portal, right? The My Campus portal. Does everybody know what I'm talking about?
Yes.
Okay. So I can install a role, a deployment role. I can tell this server that, and right now I'm using it for DNS and I'm using it for Internet Information Service, right? But I can take a server, Microsoft server, and I can basically add this right here. Does everybody see this?
Yeah.
Active Directory what? certificate
Certificates.
services. When you check that box, you turn this server into a public key infrastructure resource. What am I saying? Have you ever been to a website where it says, hey, this certificate's out of date or unknown? Have you ever been
Yes.
to? Yeah, okay. What I'm trying to tell you is that the certificate services, it turns this system into a certificate authority, which is trusted by other systems, right? So there's a trust relationship that's implemented. When you implement this role, when you deploy this role, you turn the server into a certificate authority that runs certificate services. In simple terms, you turn on PKI, and that allows you to control whether certificates are expired, whether they need to be revoked, how long the certificates are good, what kind of keys are used inside the certificates. The same thing that you use in your websites for padlocks, for certificates, to encrypt information to and from. Now here's the kicker, and this is the last part of it that's actually ingenious. When you're working to connect to a website, you're using public-private key pairs. And what those public-private key pairs embedded in the certificate transmit back and forth are symmetric keys. Let's say that again. When you connect to a padlocked website that uses TLS, I'm oversimplifying here, it's using public-private key pairs and certificates, and it establishes the connection, and the first thing they exchange are encrypted versions of the symmetric keys for the server and for the client that's connected. There's a different symmetric key for each web connection, for each client connection, which is why you're able to do things with streaming media on a website so efficiently. If the only form of encryption you had was the public-private exchange, those are very slow, but they help exchange symmetric keys securely so that you can encrypt the data between the website and your web browser, okay? So I want you to understand the relationship between symmetric ciphers and how they're the original encryption method, how distributing the keys securely is a problem, how having the public-private key pair is a new twist that solves the problem. Because you can exchange public keys with anybody, and then you can establish an exchange of encrypted information, and if that first exchange is symmetric keys between one-time only symmetric keys, not to be duplicated, only two copies, sending and receiving end, right? Now you have a way to set up an encrypted channel with symmetric keys, and those were distributed when the public-private key pair engaged with the certificates. And Microsoft has all that stuff built in, so you can set it up by just clicking a button and then setting up, well, there's a little bit more to it, but you have to set up a root certificate, and then there's a trust relationship that's established, but then everybody knows who you are. When you have websites where that hasn't been done and people haven't done their homework, nobody knows who they are, you get these error messages in the browser. Okay, this is an unknown certificate. Okay, this is an expired certificate. That's why it's so important to be careful if you connect to a website and you see that mistake, that error. It means the keys aren't good. So there you have it. That's a crash course in the essentials for encryption. Does anyone have any questions, or anyone have any questions, or?
Yeah, is this PowerPoint gonna be on Blackboard?
Yes.
Okay.
Yes, it is on Blackboard. In fact, it's in here and it should be inside under either the references or the resources. It's chapter 2. So when you look at this from chapter 2, that's exactly what we're looking at right now. Now, I do have a couple of slides from chapter 20. It's just section 6 of chapter 20 that talks about how the PKI works when you have certificates. You know, you have the private certificate on the server, on the certificate authority, and it's the public certificates that the server issues out to everybody. So it handles the distribution for you. That's the important thing to understand. The standard for certificates is called C3509. It's X.509 is the standard. It's in your study guide. That's a good question. Thank you for asking that. And let me make sure it's in here. And if it isn't in here, I'm going to put it in here. Any other questions?
No, that's it.
No.
There you go. There's the same slides. And then this one is about the key distribution, right? So yeah, the key distribution is there's nothing in there that that you'd have to worry about. It's mostly what we just covered here in these slides. Okay. Yeah, so there are some comparisons between the different types of public-private key methods and what they're about. I'm not going to grill you on that or require you to know all of that. You can use public-private key pairs to sign things digitally, and that's convenient because you can put out your public key. You can just attach a certificate to your email and there's your public key. That's how it's delivered, right? This is a diagram of the same thing we walked through on the screen that I just explained, right? And yeah, more diagrams about how, see, there's a private key and a public key on either side. Now it works in two directions. You can use the public key to encrypt or decrypt. You can use the private key to encrypt or decrypt. But if you encrypt with the public key, the private key has to be used to decrypt. If you encrypt with the private key, the public key has to be used to decrypt. Did everybody hear that?
Yes.
Okay. Does everybody see this signed certificate?
Yeah.
And do you see this? What's
Yeah.
in the certificate? Bob's public key. And what else? Bob's information and the certificate authority information. So the reason that the certificate is trusted is because the certificate authority from that company has been registered and they put out those certificates. And that's why you get the trusted thing on your web browser, okay? Now, if that isn't there, if somebody's doing a key, it's called a self-signed key. They're generating a certificate, a self-signed certificate, but there's no certificate authority. There's no registration or trust that's established. So you can create self-signed certificates on your system, and there's actually some really easy YouTube videos that show you how to do that. The only problem is if you send that certificate out to somebody, they're going to go, I don't know who XYZ such and such is, right? You know, so that's the whole benefit of having public key infrastructure. There's a trust relationship that's established that signs that certificate with Bob's public key. And also the certificate's public key. So your web browser goes, I don't know Bob, but I know the certificate authority that trusts Bob. So that's what I mean by trust is established, right? Bob's certificate is actually signed by the public key infrastructure server, the CA, the certificate authority. And then because your web browser recognizes all of the big VeriSign. There's all of these different brand names that are involved. Your browser is updated with new versions of the certificate authorities. And if your browser is out of date, it doesn't have the updated versions of the certificate authorities. That's how you know whether or not a website is secure. Does that make sense?
Yeah.
So the CA trusts are built into the web browser updates. And it's the certificate authorities that sign the public key certificates for the individuals. That's why Bob can send his public key out and they go, oh, I see Bob as VeriSign. I see Bob as Thought, or, and there's 100 names, but those are the big ones. So it's fascinating stuff. And if you're interested in your pursuit of a cybersecurity concentration, we can actually have a special topic in encryption where we get into this and you can create your own certificates and, you know, build your own certificate authority with a Microsoft server and then set them up on the World Wide Web with padlocks and web pages. That's the kind of thing we can teach you to do in a special topics encryption course. So, are there any other questions or comments before we close? Okay. I will post the assessment for module 3 then. All right. So in module 3 here, you'll see the module 3 assessment, and you'll have until Monday to complete that. On Friday, we'll take up our special topic on network exposures with the mini module. Okay.
Okay.
All right.
All right,
Thanks for
thank
joining
you.
us. Bye-bye for now. See you Friday.
Bye-bye.
All right. All right.